Hi folks, and today we're going to have a look at the SQA National 5 physics paper from 2018, the section 1, which is the multiple choice questions. So let's start. Which of the following is a scalar quantity? Velocity, displacement, acceleration, force, or speed? Well, at National 5 physics, we have to know a variety of scalar and vector quantities. Scalar quantities, remember, are quantities which have only size or magnitude, and they include distance, speed, mass, time, and energy. And vectors are quantities which have magnitude and direction, and they include displacement, velocity, force, and acceleration. So, as we can see here, of the ones that are listed in the question, the only one which is a scalar is answer E, speed. Question number 2. A security guard starts at the corner of a warehouse, walks round the warehouse as shown, and arrives back at the same corner. Which row in the table shows the total distance walked by the security guard and the magnitude of the displacement of the security guard from the start to the end of the walk? So, to work out total distance travelled, all we need to do is add all of the legs of the journey together, and that gives us a value of 340 metres. The total distance walked by the security guard. The displacement, though, is how far the security guard ends up from where they started. And in this situation, the security guard ends up back where they started. So their final displacement is 0 metres. So that gives us answer D. Question number 3. A ball is thrown vertically upwards. The ball reaches its maximum height. Which of the following describes the forces acting on the ball at this instant? So, let's think about the ball. When it's thrown upwards from the thrower's hand, as the ball's moving up the way, up in the air, there is the weight of the ball, the force of gravity acting on the ball, acting downwards, and there's a force of friction acting in the opposite direction to which the ball is moving. As the ball gets higher, the ball slows down. So it will have less and less frictional force due to its velocity, its upward velocity decreasing until it gets to its highest point. And at that point there, it instantaneously stops. It changes direction, so its speed drops to 0. If it's not moving instantaneously, then there is no friction acting on the ball at that point. The only force acting on the ball at that point is its weight acting downwards. And then as it begins to fall, the force of friction starts to increase again, but because it's moving in a downward direction, the force of friction acts in the opposite direction, so force of friction is upwards, and then as it falls, that force of friction gets greater and greater, until, of course, the force of friction is equal in size to the weight acting downwards, at which point the ball will continue to fall at a steady speed because the forces will be balanced. Anyway, the question is asking us what happens to the ball at its maximum height. And obviously, the only force acting on it at its maximum height is the weight. So the only force acting is a downward force, its weight. Number 4. A motor is used to apply a force of 120 newtons to a box of mass 30 kilograms. The box moves at a constant speed across a horizontal surface. The box moves a distance of 25 metres in 5 seconds. Which row in the table shows the work done on the box and the minimum output power of the motor? So, first of all, work done. The formula is work done equals force times distance. The force acting on the box is 120 newtons. The distance it's moved is 25 metres. That gives us a work done of 3,000 joules. Power is the amount of energy transferred per unit of time. Energy over time. The energy expended is 3,000 joules, as we've just worked out, and the time it takes to do this is 5 seconds. So 3,000 divided by 5, which is 600 watts, which gives us a final answer of answer C. Question number 5. A galaxy is a collection of stars. There is no other option here. That's just one of those definitions that we need to understand and know. Number 6. The communication satellite Iridium 124 has a period of 97 minutes and an orbital height of 630 kilometers. The geostationary satellite Astra 5B has a period of 1,440 minutes and an orbital height of 36,000 kilometers. A satellite with an orbital height of 23,000 kilometers has a period of... So, in this situation, we need to notice that Iridium 124, orbiting at a height of 630 kilometers, and the geostationary satellite is orbiting at a height of 36,000 kilometers. This third satellite that we're asked to discuss is orbiting at a height of 23,000 kilometers. That is a height in between Iridium 124 and Astra 5B. Because its orbital height is in between those two satellites, its orbital period will be in between the period of those two satellites as well. Therefore, its period must be greater than 97 minutes, but less than 1,440 minutes. And the only answer in the list of options that satisfies that criteria is answer C, 835 minutes. Number 7. Far out in space, the rocket engine of a space probe is switched on for a short time, causing it to accelerate. When the engine is then switched off, the probe will... So, we need to remember Newton's first law, which says an object will remain at rest or continue at a constant speed unless it acted on by an unbalanced force. Now, when the rocket engine is turned off, because it's in space, there is no friction acting on it, therefore there is no force acting on the rocket at all. Since there is no force acting on it, there is no unbalanced force acting on it, therefore it will remain at rest or continue at a constant speed. Therefore, answer B, move at a constant speed. Question number 8. A spacecraft lands on a distant planet. The gravitational field strength on this planet is 14 newtons per kilogram. Which row in the table shows the mass and weight of the spacecraft on this planet comparing to the mass and weight of the spacecraft on Earth? So, mass has to do with the amount of matter inside of an object. So, the spacecraft will have contained a certain amount of matter on Earth. When it gets to this unknown planet, it will have the same matter in it, therefore its mass will be the same. Its weight, though, because the gravitational field strength on this planet is 14 newtons per kilogram, that is greater than the gravitational field strength on Earth, which is 9.8 newtons per kilogram. Therefore, its weight on this planet will be greater. So, mass is the same, weight is greater. Answer A. Question number 9. The distance from the Sun to the star Sirius is 8.6 light years. This distance is equivalent to, so we're going to use the formula speed equals distance over time, or distance equals speed times time. And the speed that we're going to use, excuse me, is the speed of light, 3 times 10 to the power of 8 meters per second. And the time that we're going to use is 8.6 years, but converted into seconds. And to do that, we take our 8.6 years, we multiply it by the number of days in a year, 365.25. We multiply that by the number of hours in a day, 24. We multiply that by the number of minutes in an hour, 60. And then we multiply that by the number of seconds in a minute, 60 again. And that gives us a value of 8.1 times 10 to the power of 16 meters, which is answer D. Question 10. Light from a star is split into a line spectrum of different colours. The line spectrum from the star is shown along with the line spectrum of elements X, Y, and Z. The elements present in this star are... So, what we need to do is match up the lines in the line spectrum from the star with lines on the element spectrums, or spectra rather. So if we draw some lines, in your exam I would recommend you use a ruler to do this, and you match up the lines in the line spectrum from the star with the lines on the element spectra. And as you can see there, working from left to right, the first line matches up with one of the lines in element Y, and indeed element Y's lines all match up with lines within the spectra. The second line, two double lines, faint double lines there, they match up with two lines in element X. They also appear almost to line up with lines in element Z, but the lines in element X all match up with lines present in the star. Element Z, the two double lines on the far left do appear to match, and the dark line on the far right does appear to match for element Z. But the dark line in the middle of element Z is not present in the star, and therefore element Z is not present. The only two that are present are elements X and Y. So that's answer C. Question 11. A student makes the following statements about AC and DC circuits. Firstly, in an AC circuit, the direction of the current changes regularly. That is true. In a DC circuit, negative charges flow in one direction only. That is also true. And in an AC circuit, the size of the current varies with time. And that is also true. So the answer is E. 1, 2, and 3 are all correct statements. Number 12. An electron exists around 2-point charges Q and R. The diagram shows the path taken by a charged particle as it travels through the field. The motion of the particle is as shown. Which row in the table identifies the charge on the particle, the charge on Q, and the charge on R? So we can see here the particle is moving from left to right across the screen, and then it comes into the electrical field provided by Q. And you can see it's deflected by Q by being pulled towards Q. Since the particle is attracted to Q, it must have the opposite charge to Q. So whatever charge the particle has, if the particle is positive, then Q must be negative, or if the particle is negative, Q must be positive. Then the particle moves on towards R, and when it gets to R, its direction is changed again by being pushed away from R, repelled away from R. Since it's repelled from R, the particle must have the same charge as R. So we are looking along the line here. If the particle is a positive particle, then Q must be negative and R must be positive. If the particle is negative, then Q must be positive and R must be negative. So the only option that satisfies that is option D, which is positive, negative, positive. Number 13. A transistor switching circuit is set up as shown. The variable resistor is adjusted until the LED switches off. The temperature of the thermistor is now increased. The resistance of the thermistor decreases as the temperature increases. Which row in the table describes the effect of this change on the voltage across the thermistor, the voltage across the variable resistor, and whether the LED stays off or switches on? So, quite complicated. Here we have effectively a potential divider with R1 and R2. And the supply voltage will be split between R1, giving us V1, and R2, giving us V2. So the voltage across the thermistor plus the voltage across the variable resistor must equal the supply voltage at all times. So what's going to happen here? Well, as the temperature of the thermistor is increased, the resistance of the thermistor decreases. If the resistance of the thermistor is decreasing, that means the voltage across the thermistor is also decreasing. Now, what effect does this have on the voltage across the variable resistor? As we said, if this is a potential divider, the supply voltage is split between V1 and V2. If the voltage across the thermistor is decreasing, therefore, then voltage 2, the voltage across the variable resistor, must increase to compensate for that. Now, in this type of circuit, it is the bottom voltage, the base emitter voltage as it's called, the bottom voltage on the potential divider, which controls what happens in the transistor switch. And since the voltage across the variable resistor is increasing, it is more likely that the transistor will turn on, because when the voltage across the bottom resistor goes above the switching voltage of the transistor, usually 0.7 volts in this case, it will turn on. So if the voltage across the variable resistor increases, it's likely the transistor will turn on, and that in turn will turn the LED on. So we have the voltage decreasing, voltage increasing, and switching on. Answer A. Question number 14. 3 resistors are connected as shown. The resistance between X and Y is, so we've got two 12 ohm resistors in parallel, and they in turn are in series with another 12 ohm resistor. In circuits like this, what we have to do is we have to turn it into either a series circuit or a parallel circuit. So we have a series circuit with a smaller parallel bit inside of it. So we need to turn that parallel bit on the inside into a single resistor that we can then add on in series. So this bit here, first of all, they're in parallel. For a parallel circuit, 1 over RT equals 1 over R1 plus 1 over R2. So 1 over RT is 1 over 12 plus 1 over 12. 1 over RT, therefore, is going to be 2 over 12. So RT is 6 ohms. So these two 12 ohm resistors in parallel have a total resistance of 6 ohms, which brings us to a useful little coincidence, which, if we can remember it, saves us a little bit of time from time to time. And that is, if we've got two identical resistors arranged in a parallel circuit, then the total resistance of those two resistors will be half as much as one on its own. In this case, half of 12 is 6. So we could have cut out having to do that calculation if we'd noticed that to begin with. Then this arrangement of two 12s, which makes 6 in parallel, is now in series with the other 12 ohm resistor. So we need to apply the series circuit formula. 12 plus 6, which is 18 ohms. Answer C. Question 15. The filament of a lamp has a resistance of 4 ohms. The lamp is connected to a 12 volt supply. The power developed by the lamp is, so power equals V squared over R. Straightforward formula from our formula sheet. We've got V, we've got R, so we just plug our numbers into the formula and we get a value of 36 watts. Answer B. Question 16. A block of wax is initially in the solid state. The block of wax is then heated. The graph shows how the temperature of the wax changes with time. The melting point of the wax is, so what does this graph show us? Well, initially the wax is at 20 degrees, and you can see there's these two steps in the graph. These steps relate to the melting and then the boiling of the gas. So effectively, in this situation, the block of wax is a solid from 20 degrees up to 40 degrees. Then it melts at 40 degrees and becomes a liquid. It then heats up as a liquid from 40 degrees up to 70 degrees, and then it will start to boil and turn into a gas. And then finally, it will start to heat up as a gas above that temperature. However, the question is asking us what is the melting point of the wax, and as we can see there, that is 40 degrees Celsius. Question 17. The pressure of the air outside an aircraft is 0.4 times 10 to the power 5 pascals. The air pressure inside the aircraft is 1 times 10 to the power 5 pascals. The area of the cabin door is 2 square meters. The outward force on the door due to the pressure difference is... So the pressure difference causes this force. Okay, pressure equals force over area. So the force is caused by the pressure difference in this case. So the pressure that we're using in this formula is basically the difference in pressure between the outside and inside. And that gives us a value of 1.2 times 10 to the power 5 newtons. We could have done this in a slightly longer way and used the same pressure equals force over area formula to work out the outward force due to the pressure of the air inside the cabin, and then the inward force due to the pressure of the air outside of the cabin, and then subtract them. And in that case, you would have got exactly the same answer, 1.2 times 10 to the power 5 newtons, which is answer C. Question 18. A solid at a temperature of minus 20 Celsius is heated until it becomes a liquid at 70 Celsius. The temperature change in Kelvin is... Sometimes people get confused here because they think, well, 20 up to 70 Celsius, well, that's 90. And 90 Celsius, I need to now convert that 90 Celsius into Kelvin. And that's not correct. What we need to do to think about this, let's think about 20 Celsius first of all. Convert 20 Celsius into Kelvin. Sorry, minus 20 Celsius into Kelvin. So to convert to Kelvin, we add 273 degrees and we get 253 Kelvin. The 70 degrees Celsius, change to Kelvin, add 273 and we get 343 Kelvin. So that gives us a change of 90 Kelvin. The change in temperature is the same, regardless if we're dealing with Kelvin temperature or Celsius temperature. Okay, the absolute temperature will change, but the difference in temperatures does not. Incidentally, if we want to change from Celsius to Kelvin, a nice way to remember how to change from Celsius to Kelvin, if I write the letter C, if I want to change that letter C into something that resembles a letter K, I can add a vertical line to it. If I want to go from that from that K back to a C again, I can delete that line. So I turn my C to a K by adding and go from a K to a C by subtracting. Adding to get to Kelvin, subtracting to get to Celsius. That's just a useful way of remembering. Anyway, the answer was B, 90 Kelvin. Question 19. A sealed bicycle pump contains 4 times 10 to the power minus 5 cubic meters of air at a pressure of 1.2 times 10 to the power 5 pascals. The piston of the pump is pushed in until the volume of the air in the pump is reduced to 0.8 times 10 to the minus 5 cubic meters. During this time, the temperature of the air in the pump remains constant. The pressure of the air in the pump is now... So this is a Boyle's law question. P1V1 equals P2V2. We have the initial pressure, we have the initial volume. So I've decided to just bin the times 10 to the power minus 5 bit for the time being because both the volumes and the initial pressure are all in times 10 to the power of units of times 10 to the power 5. So I just scrubbed them out. They cancel out anyway. And then just put in my values here. 1.2 times 4 equals pressure 2 times 0.8. So pressure 2 is 1.2 times 4 divided by 0.8, which gives me 6. And then I can add in my times 10 to the power 5 again at the end. And that's 6 times 10 to the power 5 pascals. Answer E. Number 20. A student makes the following statements about diffraction. Diffraction occurs when waves pass from one medium to another. Nope. The person that made that statement was thinking about refraction. 2. Waves with a longer wavelength diffract more than waves of a shorter wavelength. That is true. And microwaves diffract more than radio waves. Radio waves have the longest wavelength of all of the electromagnetic spectrum waves, and therefore of all the electromagnetic waves, radio waves diffract the most. So the only one which is correct is answer B, or is answer 2, which is answer B. Number 21. The diagram shows the electromagnetic spectrum arranged in order of increasing wavelength. Which row in the table identifies radiation R and describes its frequency? So, I remember my electromagnetic spectrum by this little mnemonic. Good xylophones usually vibrate intensely, meanwhile tambourines rattle. And that stands for gamma rays, X-rays, ultraviolet, visible light, infrared, microwaves, TV and radio waves. So, the bit of the spectrum that we're looking at here is gamma rays through to visible light. And the missing one at R is X-rays. Now, if the wavelength is increasing as we go from left to right, then the frequency is decreasing as we go from left to right, or indeed increasing as we go from right to left. So gamma rays has the highest frequency, and then X-rays, and then ultraviolet, and then visible. So the X-rays have a higher frequency than visible light. Answer A. Question 22. The energy of a water wave can be calculated using E equals rho g a squared over 2. That curly thing that looks like a P is the Greek letter rho. And that is where E is the energy of the wave in joules, rho is the density of the wave in kilograms per cubic meter, G is the gravitational field strength in newtons per kilogram, and A is the amplitude of the wave in meters. A wave out at sea has an amplitude of 3.5 meters. The density of the water is 1.02 times 10 power 3 kilograms per cubic meter. The energy of the wave is... Now, this looks like a really complicated question because there's a formula there that looks really, really complicated, and it's not something that you've ever been taught in the National 5 Physics course. However, this is a gift of a question. It's really, really easy because all you have to do is read the information that you're given and insert the values in the correct place in the formula and work out the answer. So the formula is E equals rho g a squared over 2. We look at the information that we're given, and we have the density of water, which is rho, is 1.02 times 10 to the power 3. We have G, which is the gravitational field strength, and that's 9.8 newtons per kilogram on Earth. And we have the amplitude, which is 3.5 meters. And then we just calculate it, and we get 6.1 times 10 to the power 4 joules, which is answer C. Number 23. A sample of tissue receives an equivalent dose rate of 0.4 millisieverts per hour from a source of alpha radiation. The equivalent dose received by the sample in 30 minutes is... So, equivalent dose rate, H dot equals H over T. H dot is the value that we're given, the equivalent dose rate. T is the time in minutes here. We need to convert that time into hours because we're given an equivalent dose rate in millisieverts per hour. So 30 minutes is 0.5 hours. So the equivalent dose is 0.4 times 0.5, which is 0.2 millisieverts. Answer A. Question number 24. A radioactive source has initial activity of 200 kilobecquerels. After 12 days, the activity of the source is 25 kilobecquerels. The half-life of the source is... So, we're starting at 200 kilobecquerels. After one half-life, that will have dropped to 100 kilobecquerels. Another half-life will drop that to 50 kilobecquerels, and another half-life to 25 kilobecquerels. So if we count the arrows, the number of times that activity has halved, we find it has halved 3 times. And it has done that in 12 days, 3 half-lives in 12 days. Therefore, 1 half-life is 1/3 of 12 days, which is 4 days. Answer B. And the final question. In the following passage, some words have been replaced by the letters X, Y, and Z. So, during a nuclear fusion reaction, 2 nuclei of smaller mass number combine to produce a nucleus of larger mass number. These reactions take place at very high temperatures and are important because they can release energy. Answer B. So that's the end of the question paper. I hope you found that very useful and will help you studying for your National 5 exam. I will talk to you again another time. Bye for now.